I'm Martin Conway, eventually, and I work for a company called Contomac, whom you may or may not know. We are one of the largest manufacturers of hydrogel and silicon hydrogel GP materials, as well as intraocular lens materials in the world. In fact, we produce over 20 million buttons, individual buttons, for the specialty intraocular lens and materials. Today I'd like to discuss hydrogel and silicon hydrogel materials for the specialty contact lens industry, with a particular interest on emphasis on decay. Before we start, I think we should first of all differentiate between the words permeability and transmissibility. Permeability is a property of the material itself. It's measured in units of decay, and it doesn't really reflect how much oxygen is going to flow through a given lens, because the thicker the lens is going to be, the less oxygen is going to pass through it. So we then use the term transmissibility, which is decay divided by the thickness, or decay over T. This gives a better indication of how much oxygen is available to the cornea through a given lens design and material. However, this itself can be quite confusing for the practitioner, because manufacturers will often quote a decay figure of that relates to one specific power, normally -3, and they're referring to the thinnest part of the lens, which is the central portion. So obviously this won't actually apply to what's happening over the total corneal surface underneath. However, it will give a comparative number between materials and designs over a range of products. We'll cover that later in the presentation. Soft lenses originally developed in the 1950s, soft lens materials developed in the 1950s by a Czech scientist who was trying to develop a material as a wound dressing that would allow the passage of antibiotics through the material to the wound underneath and aid healing. It didn't really work out for him, but later on the material was adopted for the use in soft contact lenses. That basic material is still used today as the backbone for most soft materials, including silicon hydrogels, and it's called hydroxyethyl methacrylate. It is shortened for HEMA. In its pure form, it contains 38.6% water and has a decay value of anywhere between 9 and 12. We'll say 11 for argument's sake. Now, these initial lenses were very, very successful when they were compared with what was available on the market at the time, which was normally just PMMA, the original Perspex lens. And patients, namely young patients, were wearing them for much longer periods of time than they were ordinarily available with the PMMA lenses. And this led to the first problems associated with them due to lack of oxygen, anoxia, such as neovascularization. And in fact, in the early 80s, a research group in Australia led by Brian Holden established that for the safety of the cornea, a given lens should actually produce no more than 4% swelling over the period of wear. This figure of 4% was settled upon because that's the average amount of swelling that was noticed in healthy eyes, young adults, overnight due to sleep without a lens present. So this was the first measure of safety for soft contact lenses. And they calculated the decay over T of 24 was required to maintain corneal health over that period. This figure was later challenged and increased by other researchers, but the industry tends to use this as a guideline. So 24 is the figure that we're looking at. clearly the conventional HEMA wasn't enough, and so we're looking at ways of boosting water content. The reason for that is it's only water that's transmitting lenses through a hydrogel, oxygen through a hydrogel lens. That's the only mechanism that it has. And those early attempts were mainly around the use of methacrylic acid, polyvinyl pyrrolidone, and glycerol methacrylate. And we'll look at what happened when we introduce those monomers to the mix. There's a direct correlation between the amount of water in a material and the amount of permeability to that material. It's almost a straight line. And in those early days, the race was on to get more and more water into the material, to the extent that there were actually materials around with 85% water content. These are incredibly fragile, as you can imagine, because we only have 15% plastic holding the lens together. The rest is water. So there had to be a balance achieved. If we look at the effects of methacrylic acid is an ionically charged monomer. It carries a negative charge. And these monomers within the matrix of the lens both have negative charges, and they tend to repel each other within the matrix of the lens. And therefore the matrix is forced apart and expanded, and this allowed more water to actually penetrate the matrix, hence increasing the water content. So the use of methacrylic acid forced the material into becoming ionic. The problem was, whilst this was a benefit within the matrix of the lens, on the surface, it meant that the surface of the lens carried an ionic charge, a negative charge. And this attracted positively charged molecules from the tear chemistry, namely protein. So these early methacrylic acid-based materials were prone to protein deposition. And so it necessitated the use of enzyme cleaners to remove this, to maintain wearability beyond about 2 to 3 months. The issues around this were solved as more frequent replacements became available. First 3-monthly replacement, and later monthly and beyond. So methacrylic acid contained solutions, materials such as methylphenol A, are still viable materials in use in frequent replacement lenses. N-vinyl pyrrolidone, NVP, is a highly hydrophilic monomer, which allowed the materials to swell up to 70% and beyond. The downside of N-vinyl pyrrolidone, that if there was any residual monomer left in the lens that hadn't fully polymerized into the matrix, it caused irritation and stinging to the patient. And also, it tended to make the lenses more prone to splitting. There were strength issues around its use. Please excuse me, I'm getting over a cold, so I'm just getting a little bit croaky. So why not keep adding water? Well, the problem is the more water in the material, the less plastic there is holding it together. And so if we look at a 38% water content material, one of the original materials with a DK around about 10 to 12, we could actually make those with a minimum center thickness of 0.03 of a millimeter. That gave us a DK over T value of 30 at its max. By increasing the water content to 55, DK almost doubled to 18, but we also had to double the thickness of the material to stop it breaking. Likewise, with 70% materials, they had to be even thicker to make them manageable and handleable by the patient. So overall, we didn't really improve the DK over T, or the transmissibility of the material. The materials became softer and kinder to the lids, but the overall transmission through the lenses didn't really improve. So another problem with these earlier lens materials was the fact that although we measured the decay when they were fully hydrated, there was never as much water available to the lens on eye as there was when they were in the vial. So the lenses tend to lose water to the atmosphere quicker than it was being replaced from the tear fluid. And so you got an overall reduction in water content and hence decay. So if we look, excuse me, this is an experiment that we did where we measured the water content of material after 8 hours wear by patients. And we can see that our 38% material ended up as 31, our 55 ended up at 43, and the 70% materials came down to 62. And the resultant decay losses, as you can see there from the graph, from the figures. So this led us on to the use of glycerol methacrylate, the GM products that we know now. Now GM is an ultra hydrophilic monomer. It hangs on to its water and is reluctant to give that up to the atmosphere. And we can see that by using GM products such as GM49 and GM58, the lens can be worn continuously for 8 hours with almost insignificant loss of water and decay. So these lenses are much more stable on the eye and much more predictable over the length of the day's wear. The other advantage of using these materials is we didn't need to wait for the lens to stabilize on the surface of the eye before we could assess the fit. With older types of materials, the lens had to be left on the eye for periods of up to 2 hours before assessment of the final fit could be made, because the lens's shape was changing as it dehydrated. With these GM products, they are stable, so assessment can be made very quickly, and we know it's going to remain as such over the period of wear. So where are we now? The optimum water content for hydrogel really is around 50 to 60% across the range. And the use of glycerol methacrylate is probably the state of the art in conventional soft hydrogel lenses. I use this slide to demonstrate the difference. As I've said, manufacturers tend to quote center thickness. This slide is from a piece of software used in the design for lathe cutting soft lenses. That yellow shade that you can see in the center of the slide is the shape that the manufacturer has to cut to allow for the swelling of the lens in the blue area, because obviously these lenses are going to expand as they are fully hydrated. So what I'm showing you here is this software has the ability to actually calculate the mean thickness across the whole of the lens, and we'll look at a more sophisticated approach later. So it means for an average lens of say a -5, an 8.6-14.5, although we ask for a center thickness of 0.15, the mean thickness across the whole of the lens, in fact the whole of the cornea, is actually 0.22. That gives us a better average as to what the transmission is going to be over that lens. I've done some calculations here based upon the Holden-Mertz criteria of a range of powers in that sort of standard format, showing the mean thicknesses as calculated by the software. And you can see that for both the 49% and the 58% lenses, they all fall well below the Holden-Mertz criteria of 24. What can we do about it? Well, this led to the advent of silicon hydrogel materials. The introduction of silicon, which transmits more oxygen than water, means that we can boost the oxygen transmission through the material without jeopardizing its strength. And so silicon hydrogels at first had to overcome the problems associated with trying to combine a naturally hydrophobic material such as silicon with a hydrophilic material of water. But once those are overcome, we can now develop silicon hydrogels. The early silicon hydrogels, such as Pure Vision and Night and Day from Alcon, were really designed to offer the practitioners a means of competing with the a rising use of laser surgery. And so they were really designed for extended periods of wear of up to 30 days. So they went for a maximum amount of silicon with minimum amount of water. Extended wear never really caught on, and also it tended to make the lenses quite stiff, and they had other problems. And so what we now have is a combination of silicon and water content. And so again, most arrive around the 60 to 70% water content, and also combining it with silicon to give us the best of both worlds. We have water carrying the oxygen through the material, boosted by the presence of silicon. Now these slides were produced by Ultravision here in the UK. And what they're doing is calculating the DK value against a thickness of a given lens design. So here we have an example of methylphycon, 55%. Sorry, okay. Basically that was that showed that the fact that if you used a silicon hydrogel material, you were going to satisfy the Holden-Mertz criteria, whereas by using a conventional silicon, you weren't.